In my previous lecture, I talked about how color images are stored in a digital format and how those images are displayed on a computer monitor. Today I'd like to talk about how those digital images are printed. I'm not talking about printing to your own personal desktop printer, so I'm not going to talk about inkjet printing or color laser printing. There are many different types of technology for printing your own personal prints, and those are too numerous to discuss here. I'm going to focus on something called offset lithography. This is a type of printing that uses plates on a printing press. This is how most items have been printed commercially for well over 100 years. So most books, newspapers, magazines, brochures, posters, product packaging are all printed with this process of offset lithography. And if you're working with clients to produce images that are destined for print output, there's a very good chance that they'll be using offset lithography. So that's the type of printing that I'm going to focus on today. I'll describe the process in more detail soon. The process of printing color images is very different from displaying them on a monitor. With a CRT or LCD monitor, the device is actually generating light and producing light that shines out to your eye. Paper, of course, does not produce light. Instead, the light is coming from other sources, such as the sun overhead or light bulbs in a room. The light reflects off of the paper surface back to your eyes, and that's how you see the image that's printed on the paper. Blank white paper reflects most of the light that hits the surface. Very little of the light is absorbed by the paper, and the paper reflects back equal amounts of red, green, and blue light, which, when it enters your eye, is perceived as white. Black paper, or paper that has black ink printed on it, absorbs most of the light and reflects very little back to the eye, and therefore it's perceived as being black. Colored paper, or colored inks printed on paper, use pigments that absorb some of the wavelengths of light and reflect others. What your eye senses is only the light that is being reflected back to your eye. Here's a way of visualizing this graphically. What you're seeing here is a sheet of paper viewed from the side with an imaginary beam of white light striking the paper and then some components of that white light reflecting back towards the eye. As we've discussed before, equal amounts of red, green, and blue light is perceived as being white. So we could say that white light consists of beams of red, green, and blue light traveling together. When this beam of white light hits white paper, equal amounts of red, green, and blue are reflected back to the viewer, and the viewer's eye perceives this as being white. When that same beam of white light strikes black pigment that's printed on the surface of the paper, the chemicals in the black pigment absorb all of those wavelengths of light, reflecting essentially nothing back towards the eye, so the image appears black. Various colored pigments absorb certain wavelengths of light and reflect others. So, for example, the chemicals in a red pigment absorb both green and blue light, reflecting only red light back to the eye, and therefore the eye perceives that surface as being red in color. Similarly, green pigment absorbs the red and the blue wavelengths of light, reflecting only the green, and a blue-colored pigment absorbs red and green light and reflects only the blue light to your eye. You might think that you could use a combination of red, green, and blue pigments to print all of the different colors in the visible spectrum, similar to the way that a computer monitor uses red, green, and blue light to create all of the colors in the visible spectrum. However, there's a problem with using these particular kinds of pigments for printing. The problem is that each of these pigments absorbs two wavelengths of light and only reflects one. And we'll see in just a second why that's a problem. So just as a reminder, red pigment absorbs green and blue and reflects red light. Green pigment absorbs red and blue and reflects green light. Blue pigment absorbs red and green and reflects blue light. When you combine any of those two pigments together, they actually absorb all of the wavelengths of light and reflect very little. So, for example, if you were to combine red pigment and green pigment, the red pigment is absorbing the green and blue, the green pigment is absorbing the red and blue, and therefore none of the wavelengths of light are actually able to reflect back to the eye. And so combining these pigments results in something that looks very dark and muddy. It does not produce the full range of colors in the visible spectrum. As far back as 1752, printers did try to use a combination of these pigments in order to print full-color images. Here's an example from Jacques Gautier from 1752, obviously a medical image that's been printed using a combination of red, green, and blue pigments. You'll notice that the image is pretty dark and muddy. And after a number of attempts using these colors of pigment, this process was abandoned because the results were not all that good. By the late 1800s, printers had discovered a trick that allowed them to print much better quality color images using different groups of pigment. They had much more success if they used pigments that absorbed only one wavelength of light and reflected the other two. Cyan pigment contains chemicals which absorb only the red wavelength of light and reflect green and blue in equal amounts. When the green and blue light strikes the eye, it is perceived as this light greenish-blue color that we call cyan. Magenta pigment contains chemicals that absorb only the green light, reflecting equal amounts of red and blue, which the eye perceives as this light sort of purpley red color. And yellow pigment absorbs only the blue light, reflecting equal amounts of red and green, which the eye perceives as a yellow color. These three colors are referred to as the subtractive primary. They're called primary colors because they can be combined to create most of the other colors in the visible spectrum. But they're referred to as subtractive because they function by absorbing or subtracting a particular wavelength of light and reflecting the other wavelengths of light. So as I've already mentioned, cyan pigment absorbs red light, reflects blue and green. Magenta pigment absorbs green light and reflects blue and red. Yellow pigment absorbs blue light and reflects green and red. Another reason that these are referred to as subtractive primary colors is because when you combine these pigments, the resulting color is always darker or less bright than either one was alone. This is very different from what we saw with the additive primaries, which are the colors of light, red, green, and blue. So notice what happens when you combine cyan and magenta. The cyan is absorbing the red light. The magenta pigment absorbs the green light. The only light that reflects back to the eye is blue. Similarly, if you combine cyan pigment and yellow pigment, the cyan pigment absorbs red, the yellow pigment absorbs blue, and only the green light is reflected back to your eye. So cyan plus yellow make green. When you mix yellow and magenta pigments, the magenta absorbs green light, the yellow pigment absorbs blue light, and only the red light is reflected back to your eye. So yellow and magenta combine to make reds. So combining these three colors of pigment allows you to create many more colors in the visible spectrum. Here we see that same phenomenon displayed graphically. At the top, cyan and magenta pigments are mixed together. The cyan pigment absorbs red light, the magenta pigment absorbs green light, and only the blue light is reflected, and so on. This process was discovered in the late 1800s and was first used commercially in the 1890s. Here you see the very first image that was widely printed and widely distributed using the cyan, magenta, and yellow printing process. It's still a little dark and muddy, but it's a huge improvement over what had come before. This process of using cyan, magenta, and yellow inks has evolved in something that we call the four-color printing process. This uses the three subtractive primaries, cyan, magenta, and yellow, and adds black as the fourth color of ink. There are a couple reasons why black was added to this process. First of all, in theory, cyan, magenta, and yellow mixed together would create black because they would absorb all wavelengths of light. But in reality, the inks are not perfectly pure, and therefore combining all three of them makes a very dark, muddy brown. It doesn't make a true black. So black was added as an additional ink for printing very dark areas of an image that had to be very dark black. Another reason why black was added is that the three colored inks, CMY, are much more expensive to produce. It's much cheaper to produce black ink. So rather than trying to make dark areas out of a combination of all three colored inks, it's much less expensive if you fill those dark areas in with just black ink. In this process, the black is represented by the letter K. and therefore we refer to this process as CMYK, cyan, magenta, yellow, and black. Some people claim that the letter K was used instead of B for black to distinguish it from the B in RGB. Turns out that's not actually true. CMYK inks were in use in the late 1800s, long before color television or color computer monitors. So in the late 1800s, nobody knew what RGB even meant. The letter K was chosen because it represents what's called the key color. It turns out in a printed image, much of the detail comes from the black information, and therefore the black was key to creating detail in a printed image. So this process of using these 4 colors of ink, CMYK, is often referred to as 4-color process printing, or simply process color printing. You can color objects in your favorite Adobe graphics software using a combination of cyan, magenta, yellow, and black inks. This is what your color picker would look like. Instead of having 3 sliders for red, green, and blue, you now have 4 sliders for cyan, magenta, yellow, and black ink. And notice that the box where you can enter a numerical value for each color is no longer arranged from 0 to 255, it's a percentage from 0 to 100%. What this means is that if you print 0 ink on paper, it means you're printing nothing. You're simply letting the white of the paper show through. If you print 100% ink on paper, it means you're covering the paper with a solid layer of ink. So notice in the center that the magenta ink has been turned all the way up to 100%. So this means that you're printing with 100% solid magenta ink in that object. Over on the right, we see what happens when you put cyan, magenta, and yellow, all 3 of them, all the way up to 100%. The image does appear black, but as we've discussed before, when this is actually printed, it would probably appear kind of a dark, muddy brown and not a true black. So you'd be much better off in this case simply sliding the K all the way up to 100% and setting CMY back down to 0 so that you would print with 100% solid black ink. Of course, you're not limited to choosing just 0% or 100% of any of these colors of ink. You can choose any percentage between 0 and 100%. So here, for example, you see 25%, 50%, or 75% magenta. And you can see how you can use these percentages to create lighter tints of each color. Plus, you can combine different amounts of cyan, magenta, yellow, and black to create essentially all of the colors in the visible spectrum. When you print one of these lighter tints of a color, the printer does not simply apply the ink more lightly to the paper. The printer can't dilute the ink or mix it with white in order to make a lighter version of the color. The only way that the printer can make a lighter version of one of these colors of ink is to create something called a halftone pattern. We've talked briefly about halftones in an earlier lecture, and you can see an example in the lower left. To create lighter areas of ink, the printer applies the ink in small dots, where the ink covers only a small area of the paper, allowing a lot of the white of the paper to show through. To create somewhat darker tints, the printer creates larger halftone dots, which occupy more of the area of the paper, allowing very little of the white of the paper to show through. This image is magnified significantly. Normally, this image would be very small, so that the individual halftone dots would not be visible to the naked eye, and yet it would still create the illusion of varying different percentages of magenta ink. When you use different percentages of all 4 colors of ink, each color is printed as its own dot pattern on the paper. You can see that in the bottom right side of the image. There's a picture of some pears, and at normal magnification, it appears as a completely continuous tone image. But when you zoom in, you realize that the image is made up of several overlapping halftone patterns of colored dots. I think you can probably make out the halftone pattern of the magenta dots, the cyan or bluish colored dots, the halftone pattern of the yellow dots, and also there's a halftone pattern of black dots as well to create the very dark areas. So to create lighter percentages of each color, you have to use these patterns of halftone dots. And to create new colors, which are combinations of the 4 different colors of ink, you have to print these halftone dot patterns on top of one another. By the way, this slide also demonstrates something that I discussed briefly in an earlier lecture. The difference in line screens between what we call a very coarse line screen, where the halftone dots are large and spaced far apart, versus a very fine line screen where the halftone dots are very tiny and the rows of dots are spaced very closely together. So here you see a comparison of a 65 line screen, which would be used for something like newspaper printing, where the dots would almost be visible to the naked eye. A 133 line screen, which is used for most types of printing, most books and packaging and posters and so on. And then 200 line screen, which would only be used for high quality art books and corporate annual reports and other types of very high quality printing. In order to print an image using CMYK inks, you have to have 4 different plates on a printing press. One plate to print the cyan information onto the paper, another plate to print the magenta ink, another for the yellow, and another for the black. These 4 different colors of ink are then printed on top of one another to create the final printed CMYK image. They're actually printed in a slightly different order. The order in which they are printed is YMCK. They always print the lightest color of ink, the yellow, first, and then black is the darkest color of ink, so they go from light to dark. So when these 4 different prints, using these 4 different colors of ink, are printed on top of one another, you get the final image like you see at the bottom. Here's a little bit more detail about how the printing process actually works. Printing ink is a very thick liquid. It is poured into an ink reservoir, and from the ink reservoir, the ink is transferred onto something called an ink cylinder. The ink cylinder, in turn, transfers the ink onto something called a plate cylinder. The plates that are responsible for printing the image are wrapped around the plate cylinder, and as the plate cylinder rotates, it picks up ink from the ink cylinder. The plate cylinder then transfers the image to another cylinder that's covered with a rubber blanket. This is known as the blanket cylinder. So the image is actually transferred from the plate cylinder to the blanket cylinder, and it's the blanket cylinder that actually then transfers the image to the paper. This process is referred to as offset lithography. The word lithography comes from the Greek word for stone, lithos, because this process was originally done using flat slabs of limestone. The plates now consist of thin sheets of aluminum, or in some cases even thin sheets of plastic or paper. The term offset refers to the fact that the image is transferred or offset from the plate cylinder to the blanket cylinder before being applied to the surface of the paper. You need one complete set of these cylinders for each of the 4 plates on the press. So you need one set of cylinders for cyan information, another set for magenta, another for yellow, and another for black. So if you look down at the bottom right corner, you'll see what a 4-color printing press looks like. And if you look closely at it, you'll notice that towards the right-hand end of the press are 4 identical-looking units. Each unit contains a complete set of the cylinders. So one of those heads, as they're called, is responsible for printing the cyan information, another for the magenta, another for yellow, and another for black. So a single sheet of paper passes through 4 sets of cylinders and is printed with 4 different images, one for each of the 4 colors, before the final print is complete. You might be wondering how it is that you obtain those 4 different plates that are used for CMYK printing. This is a fairly complex process called color separation. Color separation refers to taking a single full-color image and separating it into the 4 plates that are used for the press. This was originally done using a photographic process that dates back well over 100 years. Then the traditional process was replaced using digital technology beginning in the mid-1980s. In traditional photographic color separation, you always start with an original piece of artwork, some sort of hand-drawn, hand-painted piece of art. You place the artwork on a device called a graphic arts camera, and you can see a picture of a graphic arts camera in the lower right. These are very large, antique-looking contraptions. The artwork would be placed on that flat board at the far right, and there's a set of lights that illuminate the artwork on that board. And then there's a very large camera that is used to photograph the artwork not once, but 4 different times. Each time the camera takes a photograph, a different colored filter is placed in front of the lens to filter out certain wavelengths of light. In the end, this produces 4 different negatives that correspond to the 4 different colors of the 4-color process. In another photographic process, each of those 4 negatives is used to burn a plate. What I mean by that is a plate is actually a piece of metal or plastic or paper material that has a photosensitive coating on it, and the negatives are placed over the plate, it's exposed to light, and that actually burns the image into the surface of the plate. The result is that you have these 4 different negatives, one for each of the 4 colors of ink, and the film negatives are then used to burn the 4 plates that go on the press. In digital color separation, you start with a digital image in CMYK color format. You might create the image from scratch in CMYK. For example, I create all of my Adobe Illustrator artwork in CMYK. Or you may have an RGB image that has to be converted into CMYK. So for example, if you scan something into the computer, typically you're going to scan it in RGB, and later you have to convert it from RGB into CMYK. Or if you render something from a 3D modeling program, chances are the rendering is going to be an RGB image, which later has to get translated into CMYK format. From this CMYK digital file, you can print out 4 film negatives on a device called an image setter. That large machine you see at the bottom of the slide is an image setter. It has a computer processing unit attached to it, and the image setter actually contains a laser which etches the image onto a photographic negative. The end result is you have 4 negatives which you can then use to create plates that go on the press, very much like in the traditional process. Or there are newer devices called plate setters that allow you to use a laser to print directly on the plates, so you skip the entire step of producing film negatives. You literally hit print on your computer, it sends the digital file to the plate setter and spits out 4 plates that are ready to put right onto the press. So once again, you start out with your full color image, a CMYK image, and you spit out 4 plates, either 4 film negatives that are used to produce plates, or using a plate setter, you would image this directly to those 4 plates. But these would still get placed on a press. You'd still have a 4-color printer to print 4 different colors of ink to get your finished printed image. As I mentioned earlier, anytime you scan something, typically you are scanning in RGB color. Likewise, all digital photographs are in RGB color. And many of the images that you create in your favorite graphics software are also going to be in RGB format. So images rendered from a 3D program are typically in RGB, or you may create RGB images in your favorite raster software like Photoshop or Painter. Regardless of where the RGB image comes from, it has to be converted from RGB format into CMYK format before you can print color separations. You may be aware that in Photoshop, you can go up to the Image menu, go to a submenu called Mode, and if you have an RGB file, you can simply change the image mode from RGB to CMYK. The process seems very simple. However, in reality, this conversion from RGB to CMYK is not simple at all. There are 2 reasons why it's actually much more complex than it would seem. First of all, RGB and CMYK devices have different gamuts. You may recall in an earlier lecture we talked about the notion of a gamut. I'll explain that again in just a second. Also, this process of conversion from RGB to CMYK is controlled by very complex color settings within the software. And if you don't know what those color settings are, or if you haven't set them properly, your conversion from RGB to CMYK may not turn out very good. So we'll talk a little bit about that as well. In an earlier lecture, I talked about the notion of gamut. Remember that this large colored circle is supposed to represent all of the colors that exist in the visible spectrum. There is no mechanical device that can reproduce absolutely every color that exists in the visible spectrum. RGB monitors are not perfect, and they can't reproduce every color in the visible spectrum. So we draw this line called an RGB gamut that shows the limited range of colors that can be reproduced using an RGB device like a computer monitor. Well, it turns out that printing devices also have a type of gamut. CMYK printing presses cannot reproduce all of the colors in the visible spectrum. In fact, the CMYK gamut is smaller than the RGB gamut, meaning that there are many colors that exist in the RGB universe which cannot be reproduced in CMYK. To put it another way, there are colors that you see on your computer monitor that you simply cannot reproduce using a CMYK print. So in this graphic, any color that falls inside the RGB gamut but falls outside of the CMYK gamut is a color that you could see on your monitor that cannot be reproduced in CMYK. When you convert an image from RGB color to CMYK, many of those colors that fall outside the CMYK gamut are going to change. They're going to move from the RGB space into the CMYK space, and the computer will try to replicate the color with the closest possible CMYK match. Unfortunately, sometimes the CMYK color, which is the closest match, is still not a very good match. Here's an example. On the left are a group of RGB colors. On the right, you see what those same colors look like after translating them into CMYK. Some of them look pretty good. The gold in the upper left corner looks pretty much the same in RGB space and CMYK space. But that bright green right next to it has changed dramatically. You can create some very vivid greens in RGB that simply can't be reproduced using CMYK color. So when you convert your image from RGB space to CMYK space, you'll often see these very dramatic color shifts or color changes. Notice the cyan square in the upper right. It becomes much darker and grayer. That vivid magenta on the left becomes very dark purple in CMYK, and so on. So the conversion from RGB to CMYK space is complicated by the fact that these two different color formats are not able to reproduce the same range of colors. So your colors may change dramatically in converting from one color space to another. You can try to avoid those ugly surprises by simply not using colors that fall outside of the CMYK space. If you know that you're going to be converting an image from RGB to CMYK at some point, then you can try to create an image that uses only colors that fall within the CMYK gamut. Now, how do you do that? In Adobe software, there's something called a gamut alarm. It's a little warning that tells you that you've chosen a color that exists in RGB space, but it cannot be produced in CMYK. In the Adobe Color Picker, if you choose a color that cannot be translated into CMYK, that little triangle with an exclamation point in it will appear next to the color swatch. This is the gamut alarm, and it tells you that this particular color looks fine in RGB, but it cannot be reproduced in CMYK. Right underneath the triangle with the exclamation point is another color swatch that shows the closest equivalent that can be reproduced in CMYK. So what you could do is click on that little square below the gamut alarm and choose a color that's going to stay the same when you convert from RGB to CMYK. It means you're still limited to using darker, duller colors, but at least you won't get any unpleasant surprises when you convert from RGB into CMYK space. Finally, this whole process of converting from RGB to CMYK is controlled by the color settings in your Adobe software. All Adobe programs have something called color settings under the Edit menu. This is where you can control how RGB colors are translated into CMYK colors. It turns out that a single set of RGB numerical values can be translated into many different CMYK values depending on how you've chosen these color settings. It's very important that you choose these color settings before converting an image from RGB to CMYK. If you don't choose the correct settings, then the conversion from RGB to CMYK may not work very well, and you may end up with very ugly colors. So you have to understand these color settings and choose the correct ones before you convert images from RGB to CMYK. In the Adobe color settings, you have to choose two different settings. One is called the RGB color profile. The other is the CMYK color profile. We'll talk a lot more about this in class, and I'll explain exactly what these sets of color profiles are all about. For now, I'd just like to show you what the Adobe color settings look like and describe them briefly. As I mentioned earlier, you go under the Edit menu and you choose Color Settings, and you'll see a dialog box that looks like this. Notice at the very top where it says Settings, there are a group of presets. These are groups of color settings that are designed for different kinds of work intended for different types of output. So for example, there are color settings specifically for creating artwork for use on the internet. There are other presets that are designed for different types of printing. In this example, I've chosen something called North American Prepress 2. This is a group of color settings that's designed specifically if you're creating artwork that's intended for offset lithography being done in North America. It turns out that offset lithography is done just a little bit differently in different regions of the world. So there are other presets that are designed for offset lithography being done in Europe, and another set for offset lithography in Asia. And even within offset lithography, there are different variations. For example, printing on newsprint is very different from printing on coated paper. So there are actually different color settings that you would choose if you're creating artwork that's destined for those different types of paper. The color settings take into account things like the absorbency of the paper, the dot gain of the ink when it hits the paper, and other phenomena that are unique to that particular type of printing. So as I said, we'll discuss this in a lot more detail in class, and I'll show you which are the common settings that you would choose for different types of work, whether it's work designed for the web or work designed for print.